Hey guys, lesson 12, two more to go. These two lessons will be talking about the last chapter, chapter 6 that we skipped before. The topic is linear programming. Those of you who are doing computer science might be familiar with it. In this lesson today, we will cover the first 3 points about the formulating a problem and then illustrating it graphically. And we will also look at the method how to find out the optimal solution. There are two methods. Today we will be talking about the ruler method or the objective line method. So linear programming is the recently formed area of mathematics with quite important applications in real life. This method or its method are used for maximizing or minimizing the values of the variables that are subject to constraints or limitations. Usually it is applied to maximize the profit or minimizing the cost given the constraints on time or material and so on. There is some basic vocabulary that you should be familiar with. The first one is obviously decision variables. Those are the number of things that are involved in the problem and that can be obviously varied. Then we have an objective function. That is the function that describes your objective. That's what you want to do. Either you want to maximize something or you want to minimize something. Then we have the constraints. As I said before, those are the limitations that prevent you from using an infinite number of each of the variable. Then we have a feasible solution. That is a solution or the values of the decision variables that satisfy each of the constraints. Then you have a feasible region. That is the area or the region on the graph that contains all of the feasible solution. And then you have the optimal solution, which is a feasible solution that meets the objective. So the first point that we need to look at is how to formulate a linear programming problem. Basically, it has a few steps during which you need to translate the text into the form of mathematics, inequalities, or define the objective functions. So the first step is you need to define the variables, state clearly on your paper or in your solution which variable stands for which object in the problem. Then you need to state the objective function. That means what you want to do, what you want to achieve. And at the end, write the constraints as inequalities. So for example, when we look at example 1, Alex is buying some cows and sheep for his farm. Cows cost 120 pounds each and sheep 200 pounds each. He wants at least 10 animals in total. He wants more sheep than cows and he has a maximum 1800 pounds to spend. And we need to translate this into the form of the linear programming problem. That means we need to form the inequalities. So the first thing, we know that he wants to buy at least 10 animals. That means their sum, cow plus sheep, must be greater or equal to 10. Then we know that he wants more sheep than cow. That means S is greater than cow, or C. And then he has maximum of 1800 pounds to spend. That means when I multiply the number of cows times their price and number of sheep times this price, then you will not exceed 1800. That means it must be less or equal to 1800. We didn't really need to define the variables here because they did it for us, but in case they don't, then we would just state somewhere at the beginning that C stands for cows and S stands for sheep. This should be clearly stated somewhere, either in the problem or obviously the variable that you are using in your inequalities. By the end of this chapter, when we finish the next lesson, you should be able to find a possible combination of cows and sheep that satisfy all three inequalities, and later we will also be looking at the possibilities how to maximize or minimize the objective functions stated. So we will look at how to graphically represent the problem a little later, but just to give you a general idea about how this method works and what's its purpose, we can look at the original problem from example 1. We know that we had the sum of cow and sheep had to be more or equal to 10. He wanted to buy more sheep than cow, and then he didn't have, his budget was maximum 1800 pounds. Now, when we sketch these three inequalities, and I'll show you, well, you know how to do it anyway, and how to identify the region, we are looking at a wide region that will be the region of our feasible solution. The question is, what are the possible combinations that of the sheep and cow that Alex could buy? So when we look at this point, for example, then the C, cows, are on the x-axis and sheep are on the y-axis. So this point tells me, this black little cross tells me I can buy 4 cows and 6 sheep. Or another option could be I buy 5 cows and 6 sheep. One more option, if I look at that one, I have 3 cows and 7 sheep. Now, if I know that Alex can sell the produce of each cow for 150 pounds and produce of each sheep for 450 pounds, and I know that his objective is obviously to maximize his profit, the natural question could be, how many sheep and how many cows should I buy if I want to maximize the profit? So we know that profit will be equal to 150 times the number of cows plus 450 times number of sheep. So when we look at all possible combinations that we identified, we can see that if I have 3 cows and 7 sheep, my profit would be 3,600 pounds. If I have 4 cows and 6 sheep, the profit I would make is 3,300 pounds. And then the last one, if I have 5 cows and 6 sheep, the profit would be 3,450 pounds. So obviously, if your objective is to maximize the profit, you know that you should get 3 cows and 7 sheep. So now let's look at example 2. As you can see, the real challenge in this part of the problem will not be mathematics, but it will be quick English comprehension. That means you need to read quickly through the text and be able to identify all the variables and form the inequalities. So let's just, I'll try to make this a little smaller so I have some space. And we need to read through the text. Don't forget to define the variables. You need to define it clearly, and of course you need to also include a non-negativity constraints where it's applicable. So what I know is that some chocolate factory is producing 2 kinds of handmade assortments in gold and in silver color to commemorate 50 years in business. So immediately I can define the variables. You can name it as you wish. You can name it G and S, or you can name it X and Y, or whatever other names you choose, doesn't matter. I choose X to represent the number of gold handmade assortments, number of gold assortments, and Y will represent the number of silver. Now, what I know next, so this part is done, that's fine. Next one, I know that it will take 30 minutes to make all the chocolates for one box of gold assortments and 20 minutes to make the chocolates for one box of the silver one. Further, I know it will take 12 minutes to wrap and pack the chocolates in one box of the gold assortments and 15 minutes for one box of the silver. Now, this sentence will be very important, this one, that because we know that the factory needs to make at least twice as many silver as gold assortments. And then we have the price for the gold that will make profit of 80 p's, and then the silver the profit of 60 p's. Now there are 300 hours available to make, this is important, 300 hours, and to make the chocolate, and 200 hours to wrap them. And the profit needs to be maximized. Now, actually, they told us how to name the variables here. So in case you define it at the very beginning, you can just change it, but we have it correct. X is gold and Y is the silver. So that's fine. And we need to formulate this as a linear programming problem. So we have the variables. My objective function is to maximize the profit. The profit will be made as when I sell the gold one, so 80 times the number of gold packages plus 60 times Y number of silver packages, and then this will give me the profit that will be maximized. So this part is also done. Now the constraints that I need to define, constraints, I have, what do I have? Well, I have 300 hours available to make the chocolates and 200 hours to wrap them. So I can go back to the information about making the chocolates, that means here, but be careful because it's in minutes and the constraint is expressed in hours. So either change one to like hours to minutes or minutes to hours, doesn't matter. So I will change hours to minutes. So I know that for the gold assortments, I need 30 minutes each plus 20 minutes for each silver. And I know that it cannot go over 18,000 minutes. This is your 300 hours. Then the second one will be wrapping, and I know it takes 12 minutes to wrap the gold assortments. So 12 times X plus it takes 15 minutes for the silver one. So 15 times Y. And for wrapping, I have 200 hours, that means 12,000 minutes. Now, lastly, I have this sentence that I said is very important and sometimes also might be very confusing. So there is a little tip how to translate this, because you know that there needs to be at least twice, I'm going to change the color of the pen, so at least twice as many silver as gold. So silver is Y and gold is X, and you can remember that this word twice or 3 times or 5 times or whatever always goes with the last variable in that sentence. That means twice X, 2 times X, and then you will have Y. And now when you read it, you know at least twice as many silver. That means silver must be at least twice as many. That means it must be greater or equal to 2x. Okay? And then lastly, you also must state that x and y must be greater or equal to 0, obviously, because we cannot have negative values. So let's look at the next example. Please put the popcorn away, no Coke now, take the pen to your hand, and let's try to do it together. You can pause the video and then watch it after you try to translate it. I think it will be actually faster. So in this example, we have some floral display that is required for the opening of a new building. Now, display must be at least 30 meters long, and it's to be made out of two types, type A and type B. Now, type A is 1 meter in length and costs 6 pounds, type B 1.5 meters and costs 10 pounds. This is important part, just I told you a few minutes or few seconds ago. Twice goes always with the last variable in that sentence. Okay? And then at least 6, okay, that's fine. Now, the cost is to be minimized, so this part will be also important. This is your objective function. And now defining the variables. Again, they tell you, not always, but as you can see, they tell you here. So x represents the number of, x is the number of type A, and y is the number of type B displays of B, type B. So those are my variables. Okay. Now objective function, I'll do it in red. Objective function, I know I'm going to minimize the cost, and the cost will be when I multiply 6 times x plus 10 times y, and this is your cost that will be minimized. So I have objective function, and lastly constraints. Constraints are right here. So what do I have? I know that I have to have at least 6 of type B. So y must be greater or equal to 6. Then I also know that there must be at least twice as many type A as type B. Again, twice goes with B. That means this is y, this is x. So in this case, you will have 2y, and then you have x, and when you read it one more time, you need at least twice as many type x, as many type A. That means x must be greater or equal to 2y. Now I have one more, one more constraint, because it must be at least 30 meters, and I know type A is 1 meter and type B is 1.5. So if I have x, 1 times x plus 1.5 y, when I add the length, it must be greater or equal to 30. If you prefer to work with whole numbers, then just multiply it by 2 and take 2x plus 3y is greater or equal to 60. It's the same constraint. And then of course you should have x greater or equal to 0 and y is greater or equal to 0, but because I already said y is greater or equal to 6, this one is not really needed. So let's look at one more question, and that's example 4. Now again, pause the video, read through, state or define the variables, state the objective function, and then state also the constraints. Let me read from the back. I have X is the C games and Y is the T game. So X is the number of C game and Y is number of T game. So those are my variables. They are defined. This is fine. Now I'm going to define the objective function. So I have two machines, one produce cards, both the first machine. So what do I know? What do I want? The profit. So obviously maximizing the profit, and the profit made is 1.5 pounds and 2.5 for T game. So I have 1.5 times X plus 2.5 times Y, and that will be the profit that I want to maximize. Now the constraints, I'll write them here. Oops, maybe I can change the color. So constraints. So what do I have here? Produces, both machines can only be operated for. Okay, so I know that both machines can only be operated for up to 10 hours per day. That will be one of my constraints. The first machine takes 5 minutes to produce a set of pieces for C game, 8 minutes to produce a set of pieces for T game. So for the first machine, I have 5 times X plus 8 times Y. And I know that machine cannot run over 10 hours, so it must be less or equals to 600 minutes. Then the second machine takes 8 minutes for the C game and 4 minutes for T game. So 8x plus 4y also must be less or equals to 600 minutes. Now both of them must be positive, of course. X and y must be greater or equal to 0. And now the last one that I didn't yet identify, the constraint is from this sentence, because it says that it sells at most 3 times. So 3 times, remember, it goes with the last variable in that sentence. So this is your y, this is your x. So 3y will be there, 3y, then I have x, and at most 3 times of x, the s of y. That means it must be, x must be less or equal to 3y, because x must be at the most 3 times as much as y. Okay, so those are the constraints for these problems, and then I have the whole problem defined. So the next part that we need to talk about is how to illustrate a linear programming problem graphically. So let's look at one question in example 5. We are given the problem, we are given the constraints, we are not given the objective function yet, because we just need to first be able to identify the region of the feasible solutions. So first we need to identify the lines of the boundaries of each region by replacing inequality signs with equal signs. That means I will just basically sketch the lines. If the original inequality has the equal sign included, then the line is solid or full. If there is just greater or less than without the equal sign, then the line will be dashed. That means the points on the line are not part of the feasible region. So either you can obviously plot the lines using the intercept a gradient, or find where each line intersects the axis, or just identify 2 points from the line. Then we will test the coordinate, that means the point that is not on the line, to see which side satisfies the inequality. So let's look at the first one. 2x plus y is less or equal to 30. So first I replace the inequality signs with equal, because I need to be able to identify and sketch the line. So I'll find the y-intercept will be 0, 30. Then I'll find the x-intercept, that will be 15 and 0. Plot these 2 points, plot the line. It's solid because equal sign is included in the inequality. Now you can take any point that is not on the line. I think in this case it's good to take origin because it's 0, 0, and plug it into the inequality. So you have 0 plus 0 is less than 30. This is true. That means this point belongs to that region. So I will eliminate the opposite. So the white one stays. But you can also color the ones that you want to include and just ignore the rest. That's up to you. Then second inequality, I'll change it first to equation. Y is equal to 2x. Identify either 2 points, or you can use the gradient intercept form to sketch the line. So it passing through 0, 0, and the gradient is 2. Then you have the line, and then you can test any point that is not on the line. In this case, they have chosen point 5 and 0. If you plug this 5 and 0 into the inequality, you get 0 is less than or equal to 10. What is true? That means this point belongs to the region. That means eliminate the other side, other half plane. Next one is easy because it's y is greater or equal to 6. So that means there's a horizontal line through 6. And then you obviously know which region needs to be eliminated, that is below this line. And last one, I have 2x plus 3y is greater or equal to 36. So I find the intercepts. It's 0, 12 for y-intercept, and then 18 and 0 for the x-intercept. Sketch the line, and then we're going to test one of the points. Again, it's good idea to test origin because it's not on the line. When you plug the origin coordinates of the origin into the inequality, you get 0 is greater or equal to 36. What is not true? That means origin does not belong there, and the opposite side, opposite half plane belongs to the, or satisfy the condition. That means eliminate the ones where the 0 is included. So because you had 4 inequalities, now you have 4 regions that you identify and you find their intersections. That's the white regions, or now the blue one. So this is the region of feasible solutions, or simply regions that satisfy all of these inequalities at once. So let's look at the following example 6. We need to find the coordinates of the vertices of the feasible region below. So the region was identified. I think it's the same, actually it's the same question or same region from the example 5. And we just need to identify the coordinates of each vertex. So point A, I know, is the intersection of these 2 lines, 2x and 2x plus y equals 30. Find out what is the solution of this system of equations, and then you find out that point A has coordinates 7.5 and 15. Next point, take B. Again, identify it as an intersection of 2 lines. One is y equals 6, the second one is 2x plus y equals 30. So obviously when you solve it, then you will have the point 12 and 6. Next one, C point, intersections of y equals 6, green one, and red one, 2x plus 3y equals 36. Again, solve it. If you solve it, then obviously x is 9 and y must be 6. So 9 and 6 is the C point. And then the last one, you have a D. D is the intersection of these two lines, y equals 2x and 2x plus 3y equals 36. Again, solve the system of equations and the coordinate will be 4.5 and 9. So let's look at the guided practice of this second part and second point. I think I prepared 2 examples. Again, you can pause the video and try to sketch the region of the feasible solutions, and then we can compare. I'm going to also do it, but I will do it in the PDF file so I can use the square paper or the grid. So I will just cut the picture and I will continue there. So now I have those 4 or actually 5 inequalities that I need to sketch and then be able to identify which half plane is going to be rejected and which half plane I'm going to keep. Then I find out their intersection and identify the region of feasible solution. Choose appropriate scale. So I'll put the origin here, and then this will be my x-axis and this will be my y-axis, and then I'll choose the 1 unit to be 5 little squares. So this will be 1, 2, 3, 4, 5, 6, 7, 8, and 9. And 1, 2, 3, 4, 5, 6, 7, 8. So let's start with the first one. What we need to do is to identify the at least 2 points that the line 2x plus 3y equals 18 is passing through. So I'll choose the intercept. So first intercept is 0, 6. That's the y-intercept, and x-intercept is 9 and 0. So identify those points. 0, 6 is here. 9 and 0 is here. And then sketch the line. That will be dashed because there is no equal sign in the original inequality. Obviously, you have the ruler in your hand because you have the paper I gave you and you are actually doing it right now. So I need to identify which half plane I'm going to keep and which one I'm going to reject. Good idea is to plug 0, 0 origin. So if I plug 0, 0, I'm using the origin, so then I would have 0 plus 0 is greater than 18. What is obviously not true, so no, that means 0 doesn't belong to the region I want or to the half plane I want. That means I want to keep this part and reject the second part. Then I have second one is y is equals to x. Then it's easy to sketch, but again there is no equal sign in the original inequality. That's why the line is dashed. So I have dashed line. Now I cannot use 0, 0 origin to identify, but choose one point. I'm going to choose the point 0, 1. So if I have 0 and 1, I'm going to plug it in. 1 is more than 0 or greater than 0. This is true. That means the point 0, 1, 0, 1 belongs to the 0, 1 belongs to the region I want. That means I am keeping this part, right? This part I want. Then next one is easy to sketch because it's y is less or equal to 5, so it's a horizontal line. So, and it's the solid line because there is an equal sign and it's below. That means I am keeping this part. and then of course x and y is greater or equals to 0. So if you want, you can mention it here, it's greater and it's greater. So when you want to identify the region of the feasible solution, then it would be this part and then dashed line here up to, and then dashed line on this side. So this is the region of the feasible solution or feasible region. So now example 8 is similar story. Take the second half of the paper I gave you and please do it again. You need to indicate the feasible region by labeling it R. Do not forget this because otherwise the 1 mark is off on the real exam or on the paper. Okay, so again I'm going to cut and I will switch to the PDF file. So in this example we have 4 inequalities. Again, you can choose whatever method you prefer for sketching the line and then deciding which half plane you're taking, but make sure that it's clear from your writing how did you decide. Okay, so I will choose this will be my x-axis and this will be my y-axis. So x and y, and now let's go one by one. So 2x is equals to 3y, 2x is equals to 3y. You can identify 2 points, so definitely it's the origin, and then the second point is 3 and 2. So origin is here, and 1, 2, 3, 1 and 2, so that is this point. So this will be the solid line because original inequality has the equal sign there, and now I need to decide which half plane. I can use the origin, so I'll choose the point 0 and 1 again, but you can choose whatever point. So 0, 1 I am choosing. If I plug it in to the inequality, then I have 0 is greater or equal to 3. What is not true? That means 0 and 1 do not belong to my region. So if it doesn't belong to my region, that means the opposite or second half plane belongs there. Then I have 3x plus 4y equals 24. So 3x plus 4y is equals 24. Identify 2 points. So you can take x and y intercept, so 8, 0 and 0 and 6. 8, 0, so 4, 5, 6, 7, 8. So that would be this point. And then 0 and 6, 3, 4, 5, 6. So connect these two. And then it's the solid line because there is an equal sign. Now I can use the origin, 0, 0. So when you use the origin, you will get 0 is less or equals to 24. That is true. That means origin belongs to this region. So origin belongs there. That means I am taking this half plane. Then y is, x is greater or equal to 3. That is easy to sketch. That means this one, well, okay, good. So greater or equal to 3. That would be this part. And then y is more or equal to 1, is greater or equal to 1. So that would be, well, roughly this one. This and this is greater. So when you carefully observe, you have to be careful here, but all of the lines are solid. So that's this one, then it's greater or equal to 3, this, and then this one. So this is your region R. And now the last problem or last part of this lesson is locating the optimal point in feasible region. As I said at the beginning, we have 2 methods how to do it. The first one is called objective line or ruler method. So also pay attention to this because in some cases on the exam, they tell you which method you need to use, and then if you use the other one, then you will not receive the credit for that. In the problems of the linear programming, you must be able to sketch quickly the graph or the line of an equation where intercept is a variable. For example, when you consider 3x plus 5y equals c, and you can obviously express it in the gradient intercept form, you can see that the gradient is negative 3 over 5 and the intercept is c over 5. But gradient you know, the intercept you do not know because it's a function of c. As c varied, so will the intercept, but the gradient obviously stay constant. So what's the outcome of this is whatever the value of c, you will get the parallel lines because obviously the lines that are parallel have the same gradient. So if you want to draw 3x plus 5y equals c, then you basically draw any line with a gradient of negative 3 over 5. So when we look at it, anytime you will be giving the objective functions, or you will actually state the objective function, you just identify the gradient and then draw the line with the same gradient. So if you have minus a over b, that means you have a is the rise, that means on the y-axis, and then the b is on the x-axis, and because it's a negative, it's going downward. So for example, this line or this function, the objective function 3x plus 5y is equals to c, has gradient minus 3 over 5. So you can either sketch the little triangle, 3 units on the y-axis, 5 units on the x-axis, but you can obviously use a larger similar triangle, right? You can use 12 and 20 if you multiply both sides by 4. Everything depends on the scale that you are using in your graph, right? You can also use 300 and 500 if that's your scale on the axis. Depending on the scale, this may be faster than when you're going to identify the 2 points and so, but you can use whatever method you prefer. So let's look at example 9. For each axis, show a suitable line of the equation. So that's the equation we've just been talking about. So for example, if you have the axis with a scale of 1 and up to 10 on x and y axis, it's good idea to use the 3 and 5, the gradient 3 on the y-axis and 5 units on the x-axis, or you can use a similar triangle 6 and 10. So whether you draw 6 and 10 or you draw 3 and 5 doesn't matter, because it's just the initial line that you will be moving, as you will see in a moment. However, if I'm going to use a different scale, that means 140, obviously drawing 3 and 5 or 6 and 10 might not be as suitable as when you will draw 30 and 50, because it's obviously easier to see and it's not very close to the origin. I mean, it's a nice and visible line. So let's look at example 10. John makes £1 profit for every chocolate brownie he sells and £2 for every muffin. If we use x as the number of brownies and y as the number of muffins, what's the equation for his total profit P? So it's obvious that you need to multiply the number of brownies by its price. And so 1 times x plus 2 times y, and that will give you the profit. Now the question is, if he needs to make a profit of £120, what combination could he sell? So there are many combinations that will satisfy this equation. One of them is 0-60, 0 brownies and 60 muffins, or 20 brownies, 50 muffins, 40 and 40, 60 brownies, 30 muffins, and so on. So all of these points lies on this line, x plus 2y is equals 120. So you can make the line. You know that the slope or the gradient is minus 1 over 2. If you express y out of this equation, then it will be minus 1 over 2. But because of my scale, if I multiply both by 60, I will get 60 and then 120 on the x-axis. So next one is if he wants to make a profit of 180. So the gradient doesn't change. So it must be the line that is parallel to the first one that we sketched. The only things that will change will be the y-intercept. And in this case, it would be y-intercept of 90. But the line will stay parallel. So the next one is if the profit is 240. If it's 240, then the gradient is not changing. The y-intercept would be 120. Okay, and then if you want to, you can realize that if you want to increase the profit, the objective line is moving away from the origin. Okay, this will be very handy and very useful in the problems that are coming, because we will be asked to identify the optimal solution, where we're going to use this method. That's why it's called ruler method, because on your paper you are actually moving ruler in the direction that is or in the sense that the ruler will stay parallel to the original line or the first initial line that you sketched. Let's look at some problems. So we will have the same profit. We're going to maximize the profit, and the feasibility region is given below. So that's the white part. Okay. Now use the objective line method. Remember what I said before. You need to follow, or you need to use the method that you are asked to use, because otherwise you will not receive any mark. So if I'm maximizing profit, x plus 2y, the original things that the original line, the first thing what you will do is you will sketch x plus 2y equals p. So in this case, that's the one that we have done before. You know the gradient is minus 1 over 2. Look at the scale, minus 1 over 2, that would be too small, but you can use 10 and 20. So 10 and 20, then you sketch the line, that's the initial line. And now, because you are maximizing the profit, you're going to take the ruler and move it away from the origin, but be careful that the line stays parallel to the original line that you have sketched originally. And you're going to move it until you're not going to reach the last point within the critical region, because this is the point of your optimal solution, or this point represents the optimal solution. So you know that the optimal combination, if we talk about the muffins and brownies or whatever else, the optimal combination would be x would have to have the value 10 and y would have to have a value 10. Then you know the profit would be 30. Whether it's in thousands or pounds, it doesn't matter. It depends on the context of the problem. So let's look at the guided practice, the last one for this lesson. There are 2 questions that you can try on your own, and then you can play the video. So the region is given below. We need to use the objective line method to identify the optimum solution if the aim is to maximize the n. So you can identify first the correct gradient and draw a suitable line with this gradient. So you know the gradient is minus 3. That means the triangle will be 3 on the y-axis and 1 on the x-axis. So if you look at the scale, you could draw 3 and 1, but the line would be in the lower corner close to the origin, and it would be kind of short, but feel free to do it. I think it's better to use 12 and 4 with this scale on the picture. So if you have 12 on the y-axis and 4 on the x-axis, then this is your initial line. You know that you need to maximize the n, that means increasing the profit, and you also know that when you are increasing the profit you have to move away from the origin and you have to keep the line parallel. So you keep going until you're not going to meet the last point of the feasible region, because this last point within the critical region is the optimum point. So in this case it has the coordinates 20 for the x and y is equals to 0. So if you plug it in to the n, you find out the maximum value of n is 60. And let's do one more where we're going to minimize the variable m. So the region, the feasible region is the same, except I have a different objective function. So again, look at the scale. Scale didn't change, but I have a gradient that is, the correct gradient is 200, 200, or it's basically -1. But if you're just going to draw one on the x-axis and one on the y-axis, then it will be really, really small and very difficult to see. 200, 200 is for this scale also not suitable, but what you can use is 12 and 12 or 6 and 6. Okay, so if you use 12 and 12, that will be your initial line. Now you know you need to minimize the value of the variable m if it represents the cost, so you know you need to move towards the origin while you will keep the line parallel with the initial line that you sketched. Now remember, before I said you can do 6 and 6, but if you connect 6 and 6, the gradient would be okay, but it's outside of the region, so eventually you would have to move it a little bit up. That's why 12 and 12 was a better choice. Now I have my initial line and I know I need to move it towards the origin now until I'm not going to meet the last point from the feasible region. So in this case, when I move it just a little bit down, and then this is the point that I need to identify because it's the last within the critical region or feasible region. However, in this case, I can't estimate, or I cannot actually find the precise coordinates of this point, because it's not the coordinates are not the whole numbers. So we need to solve the simultaneous equations as we have done in the one of the examples at the beginning of the lesson. So in this case, you would need to know the equation of the blue line and purple line and solve the simultaneous equations to find the values for the coordinates of this point that represents the optimal solution. So this one was the last example for today. Please look at sections or set 6a, 6b, and 6c. You have the graph paper. I gave you graph paper. You will need it probably for B and C. In 6a sections, you just need to state the objective functions and actually formulate the problem of the linear programming. So try it. Answers are at the back of the book, and the full work solutions are available on this website if you need to check. And then in the next lesson, we will finish and conclude this chapter as well as the whole syllabus. I'll see you on Monday. Bye-bye.